Paper is a good. So how's it going? Yeah. So in Babson's class, you all talked about polar coordinates some more yesterday, I assume, and maybe talked about finding the slope of a tangent line. But you didn't talk about area. I don't think so. At least it was not on the homework, which is too bad because like area is probably the thing that's actually kind of something you'll use in 21D, but oh well. We don't have to talk about it. You'll learn it later. Yeah. So there's not a whole lot more to say about graphing and the polar stuff, but we will say it, and then we'll use the rest of our time. Pardon me. Polar graphing is always kind of just it's a trip. So let me look here real quick. So looking at the homework assignments, some interesting problems. Where'd you go? Here. I mean, I had some problems myself too, but I just wanted there's something I specifically had that looked. It's not it. Where'd you go? Hiding things from myself again. There we go. Oh yeah. So most of the things you guys have to graph are pretty normal, except for like a couple of them. So let's look at some more polar graphing. Yeah. Co-21B. Today is June 3rd. Yeah, June 3rd. Actually, one other thing aside before we get going, I just want to point out to all of you that there is on Canvas, if you look on Canvas, not here, real quick, let's go to our class. Sorry, one moment. If you go to our Canvas, you will see at the top of the modules a short survey to evaluate the course. If you could please all take that before the end of finals, I would greatly appreciate it. Basically, you're just giving me feedback. It's anonymous, and my supervisor reads them all and then kind of compiles the comments together and tells me about what students said. So happy to hear you say things you liked, things you didn't like, things that could be better. Obviously, for those of you in Parlax's class, you might give me some feedback about like, well, he kind of focused on the entire other class the whole time, and that wasn't really great for me. And I understand that's a fair and valid criticism. But really, if you have things to say, I would love to hear them because if you're taking Code 21C with me next quarter in fall, you might want me to do better on the things you thought I didn't do great on. And also, if you have things you like, also good to say. But really, please do fill it out when you have a second. It takes like 5 or 10 minutes, and it's not that big a deal. It is a big deal to me, so please do it. That said, and you can find it right there. Is this slide on? So polar graphing. So I'll be frank, I'm not great at polar graphing. Probably not a lot of people are, to be really honest. Like it's just not a skill that we spend a lot of time developing. Um, Last time we talked about how certain things look like circles. So I'll just give you an example. If I wanted to graph r equal to -8 sine theta. I know it's a circle. I know it's a circle because it's just a multiple of sine of theta or a multiple of cosine of theta. And here's the easiest way to graph this circle. Pick two values of theta. Specifically, you always pick theta equal to 0 and theta equal to pi over 2. If we pick theta equal to 0, you're going to get r equal to -8 sine of 0, which is 0. If you pick theta equal to pi over 2, you're going to get r equal to -8 sine of pi over 2, which is -8 times 1. So one of these, I mean, they're both actually helpful. But one of these will always give you the origin as one of your points, that one in this case. And the other one is going to give us the coordinate where we're going up -8. So we're really going down 8. So we're really down here at the rectangular coordinate 0, -8, or the polar coordinate r, theta equals -8, pi over 2. And those are the ends of a diameter of your circle. So then your circle, whoops, if it's a circle, your circle is centered halfway between the points at 0, -4. So when you ever have a multiple of sine or a multiple of cosine, you're just going to do the circle, as long as it's specifically r equal to a multiple of sine or a multiple of cosine. If you have something weird like r squared equal to a multiple of sine or cosine, then it's terrible. Which I'm not good at graphing, but I'll try to explain how you might graph that. The other type of graph we talked about last time were roses, where if I wanted to graph something like r equal to 3 cosine theta, for example, no, that's not a rose, that's a circle. I meant to say r equal to cosine of 3 theta. Since the coefficient is odd, you're going to get that many petals. So we're going to get 3 petals. And when it's an odd number of petals, one of them is always centered on an axis. And then the other two, or other however many there are, cannot be. So you usually find that by either setting theta equal to 0 or theta equal to pi over 2. Notice the common theme here. So if we set theta equal to 0 here, we get r equal to cosine of 0, which is 1. So one of the points on my polar graph here is going to be when the angle is 0 and the radius is 1. So that's where one of my petals lives. And then the other two are 360 degrees divided by 3, or 120 degrees rotated from this one. So my first one, now, normally I would draw this terribly. I mean, I probably will anyway, because, but I'm not trying to. But normally I would just be like, petal here, petal there, petal there. But I'm actually going to try and draw it out in the order we get drawn out. So check it out. From here to here, that's the section from theta equals 0 to theta equals pi over 6. Because when theta is pi over 6, your r is going to be cosine of 3 times pi over 6, which is cosine of pi over 2, which is 0. So that's half of your first lobe or petal. And then from theta equals pi over 6 to theta equals 2 pi over 6, you're going to get another half a lobe. The angles are pointing in the first quadrant of this question, or there's a chat, I should say. I'm a little confused with the positive and negatives. We're graphing in polar. Positive is upwards, the angle negative down thing. But so generally, here's how it works. You look at the angle, and then if the r value is positive, you go in that direction. If the r value is negative, you turn around and you go in that direction. So far, here's what I've graphed without saying it. When, right here, r was equal to 1 when theta was 0. And then at an angle, saying, no, there's not really, so then a smaller angle, r was a little bit smaller, smaller angle, so on. So like when theta was like, let me see here. When theta was pi over 18, for example, which is certainly between 0 and pi over 6, at theta equal to pi over, let's go pi over, sorry, brain. Sorry, guys. Pi over 9. So a 20-degree angle, pretty shallow. When theta is pi over 9, our r value is going to be cosine of 3 times pi over 9, which is cosine of pi over 3, which is 1/2. So at that shallow angle, of pi over 9, we're going a distance of 1/2. That's kind of the idea. So then, for the next section, where theta goes from pi over 6 to 2 pi over 6, or pi over 3, we'll look at what our cosine value, our R values are going to go from. Well, cosine of 3 times pi over 6 was 0. Cosine of 3 times pi over 3 is going to be cosine of pi, which is -1. So we're starting off pointing that way with an angle of 0, and then as we start pointing more and more up, our values get more and more negative. So we're actually going that way. So it's like we're coming out, and now this is where I'm probably going to blow it. Kind of like that. So right here, this is where our angle is pi over 3, and our R value is is -1. Which I really wish we wrote the angle first. It seems like it would make more sense to me. So we're pointing in the pi over 3 direction, but we have turned around and gone the opposite way. And we continue on from pi over 3 to pi over 2. Our R values are going to go from -1 back to 0, because cosine of 3 pi over 2 is equal to 0. And plugging in pi over 2 right there to get cosine of 3 pi over 2. So we're going to go back this way. And then we keep going from pi over 2 to 2 pi over 3. 2 pi over 3? Yeah. Right, so from theta equals pi over 2 to 2 pi over 3. Well, again, cosine of 3 times pi over 2 is 0. Cosine of 3 times 2 pi over 3 is cosine of 2 pi, which is +1. So in the 2 pi over 3 direction, we get a +1 value. So here's an R of 1, an angle of 2 pi over 3. And then, almost finally, from 2 pi over 3 to 5 pi over 6, we're going to get this other half of that lobe. So this part here is theta going from 2 pi over 3 to 5 pi over 6. Our R value goes from 1 back to 0. And then finally, this last half of this lobe here is when theta goes from 5 pi over 6 to pi, and cosine of 3 theta goes from 0 to -1. So we're pointing in the pi direction, but our value is -1, so we end up that way. Terrible. I feel like I gotta work out just doing all that. But you can see it'd be much easier if I was just like, oh yeah, it's a rose. It's got 3 petals. They're equally spaced out. And one of them, in this case, the first one we found, is on the positive x-axis. Cool. Question. Uh-huh. So what I'm really doing is I'm trying to let my angle go from a multiple of pi over 2 to the next multiple of pi over 2. So how I'm really breaking this down is the following way. I want my angle to go from 0 to pi over 2, bless you, to pi, to 3 pi over 2, to 2 pi, to 5 pi over 2, to 3 pi. Sorry, I kind of smushed in there. Because cosine of those numbers are zeros and ones, or -1s. They either give me where I cross the origin, or when I have the extreme of one of my petals. So at the angle of 0, cosine is 1. At the angle of pi over 2, cosine of 3 pi over 2 is 0. At the angle of, well, again, that's not really my angle though. That's the value. At cosine of pi is -1. Cosine of, right, because I'm sorry, yeah. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. Cosine of 2 pi is 1. Cosine of 5 pi over 2 is 0. Cosine of 3 pi is -1. but then I'm actually getting the actual theta values by dividing those angles by 3. 0 divided by 3 is 0. Pi over 2 divided by 3 is pi over 6. Pi divided by 3 is pi over 3. 3 pi over 2 divided by pi over 3 is pi over 2. 2 pi divided by pi over 3. Sorry, 2 pi divided by 3. 5 pi over 2 divided by 3 is 5 pi over 6. And 3 pi divided by 3 is pi. So that's where those angles are coming from. I'm basically taking my the range for theta here, and for an odd petaled leaf, theta has to go from 0 to 1 pi, not 2 pi. And in that 0 to pi, you're going to get all of your leaves. So since there were 3 leaves here, each leaf was a third of pi, and each half of a lobe was half of a third of pi, which is pi over 6. So that's why I went from 0 to pi over 6, and then pi over 6 to 2 pi over 6, 2 pi over 6 to 3 pi over 6, 3 pi over 6 to 4 pi over 6, 4 pi over 6 to 5 pi over 6, 5 pi over 6 to 6 pi over 6. But again, I'm doing too much work. If you were asked to draw this, you shouldn't do all that. Now, I will admit, it usually looks nicer when I draw it this way because I'm kind of getting it to look better because I'm following the kind of trajectory of the path. But this is after years of practice. And it's still not, I imagine some of you are much better drawers than me. So definitely don't take my drawing skills as a deterrent to you trying to draw these things. You should do the best job you can. And also, really what you should do is you should look at how they look on Desmos to get a better idea. Because if we actually pull this up on Desmos here, just a second, what did I do? I did something, wow, I don't know what I did. I hit a button and I think I was in Zoom and hit Control T and did something that I did not open a new tab as I was expecting it to do. So thankfully, we're at the point where Desmos has polar graphing. It was not always the case, but if you graph this in Desmos, R equal to cosine of 3 theta, there you go. And if you want to make it look a little bigger, you can just multiply, you can zoom in, or you can just multiply that by like 4. Well, I mean, I did a decent job, but the more lobes or petals you have, the easier it is to make it look terrible, right? Even with just 5, it's not great, right? I can't draw that, not reasonably well. I can draw it enough that you know what I meant to have drawn, and that's about it. So one thing I'll point out is all of the odd petaled cosine graphs always have their on-axis petal on the positive x-axis. Whether it's cosine of 5 theta or 7 theta or 9 theta, right? The only petal that is on an axis, and when I say on, I mean like the axis is splitting the petal in half, is the one on the positive x-axis. If you wanted to have the petal on the negative x-axis, you would need to put a negative sign in front of this whole thing. And then you would totally get that. For sine, it's not true. If you wanted to do sine of theta instead, whoop, wow, that was smooth. Sorry about that. So to find the on-axis petal here, I would pick the angle pi over 2. And then sine of 3. Oh, but it's negative out in front. I'm like, why does it look wrong? Because sine of 3 pi over 2 is negative. Sine of 3 pi over 2 is negative 1. So when my angle is pi over 2 pointing upwards, my value is negative, so I end up on the bottom. But then for sine of 5 theta, the 5-leafed one, well, if I pick my angle to be pi over 2 pointing upwards, what's sine of 5 pi over 2? Is it a positive 1 or is it a negative 1? Where's 5 pi over 2? 5 pi over 2 is all the way back around to the top. So it's going to be positive 1. Oops. Jeez. So in this one, my on-axis petal is on the positive y-axis because when I pick my angle to be positive pi over 2, sine of 5 times pi over 2 is positive 1. Whereas sine of, whereas sine of 7 times pi over 2 is negative 1. Positive 1. Whoops, that's not the number I meant to write. positive one, and so on and so on. So the sine ones alternate back and forth between being on the positive y-axis and the negative y-axis for a tonic leaf. So could you draw that? Probably. Could I draw that? No, I could not draw that. I mean, if my life depended on it, maybe, but only then. And then I'd have to try really hard. It's just hard to draw, right? But again, we know what it looks like, right? If someone said draw 4 times sine of 9 theta, you'd be like, okay, well, I'm going to find one of the points, the one that's on the positive y-axis. So, okay, you can all watch me do this poorly now. I don't think it's very elucidating, but maybe it is. So let's say someone was really, really having fun with you and said, graph uh, r equal to 4 sine of 9 theta. Okay, so I'm going to pick theta not equal to 0, although I would try either 0 or pi over 2 because that's always what I'm trying, because that's just going to give me r equal to 0 because sine of 0 is 0. So I pick theta equal to pi over 2, pointing up, my r value is going to be 4 sine of 9 pi over 2. And 9 pi over 2 is 2 pi plus pi over 2, which is the same as just sine of pi over 2, which is 1. This is going to be 4 times 1, which is 4. And then we would pray to whatever God we believe in, or none, and try to draw this thing. Ish. Okay, so I know I'm going to have one of them up here. It's probably already too wide. I've probably already blown it. Okay, it's all right. So then we'd have 8 more of them equally spaced out. I don't want to embarrass myself, but so these should be 40 degrees apart. Yeah, okay, it's about to go really wrong. 40 degrees, and then another 40 degrees puts me at 80 degrees. Boosh. And another 40 degrees puts me at 120 degrees. Ah, it's too big. And then 160 degrees. And then it's worse when it's a different number. 7's even worse. 200 degrees. Ah, 240 degrees. Oh, I'm so dumb. Oh, well. I was counting from the wrong. Oh, man. So I started at 90. So when I was adding 40, 90 plus 40 should have been 130 outside. I've blown it completely. Anyway, here's my side attempt at looks. I mean, I've drawn worse things. Let's compare. I mean, we shouldn't really, but let's see. I mean, you knew what I was trying to graph. So that's my point, is that the roses are not easy to draw. None of this is really easy to draw. And you shouldn't really need to draw much of it, I hope. But that's not really up to me. On the other hand, so one thing I will note for the odd petaled roses is your domain is theta going from 0 to pi, which is kind of interesting that you get the whole thing from 0 to pi. Whereas with the even petaled roses, theta has to go from 0 to 2 pi. So if I wanted to graph, say, r equal to sine of 2 theta, I'm going to get 2 times 2 equal to 4 petals. And what I remember about sine and cosine is for even numbers of petals, cosine you always get on axis petals, and sine they're always off axis. You never get an on axis petal. So for sine, with 4 petals, they're going to look like they're pointing and a 45-degree angle and a 135-degree angle and a 225-degree angle and whatever that angle is over there, 315 degrees. So essentially pointing this way, that way, and that way, and that way. And they all have a length of 1. So they should look something like this. Ta-da! And then first, and then for cosine, you have they're rotated essentially 45 degrees from this. So if you look at these ones, come here. Why don't you want to do the thing I want you to do? So if you look at, say, cosine of 2 theta, oh yeah, off axis, where if you, sorry, I said, sorry, if you look at sine, whereas if you look at cosine, it's on axis now. Same shape, just rotated. And that's true for, I mean, that's true for the odd ones as well. And then if you have cosine of 4 theta, you get 8 petals. Cosine of 6 theta, you get 12, and so on and so forth. And for the cosine ones, you always get 4 of them on the x and y axis. And for the sine ones, you never do. All 12 of them are off axis. So you get 3 in each quadrant, or 4 in each quadrant, and so on and so on and so on. Okay, enough of that. So today, what other graph do we have to talk about? And I forget what I always thought they were called something, but apparently they're called something else. I was looking at the textbook and I saw that, where'd you go? Sorry. So, yeah. So I always thought the things that I'm about to graph were called cardioids. But apparently cardioids are just one type of something called, I don't really care what the name is, but cardioids are a type of limaçon, the French word for snail, an old French word for snail. Because isn't the word for snail like escargot? You would think I would know, having taken many years of French and lived in France for a year, but nope. Anyway, but cardioids, or I guess more generally, snaily looking things, have graphs that look kind of like this, or I say have equations like this. This is, in my opinion, the classic cardioid. It's kind of heart-shaped is the idea here. And what I would point out is that when you're drawing a cardioid, well, in fact, let's go ahead and draw it. So here's my not so great, here's my not always, what's the word I'm looking for? This is the way I would draw it if I knew for sure what I was doing, which I know it sounds stupid, but it'll make sense when we do it. So if I'm going to graph r equals 1 plus cosine theta, I'm typically going to look at my 4 usual angles. 0, pi over 2, pi, 3 pi over 2. So you don't really have to say 2 pi because you know once you get back to 2 pi, it's going to be the same as 0. But we can put it in there anyway. So cosine of 0 is 1, 1 plus 1 is 2. Cosine of pi over 2 is 0, so 1 plus 0 is 1. Cosine of pi is negative 1, so we get 0, 1, back to 2. I'm going to plot these points. So in the angle of 0, I get an r value of 2. In the angle of pi over 2, I get an r value of 1. Pi, I get 0. 3 pi over 2, I get 1. 2 pi, I'm back to 2. And then what's happening as I go from here to here is my radial values are decreasing from 2 to 1. So it's going to look something kind of like that, where my radius is 2, and then a little less than 2, less than 2, much less than 2, getting closer and closer to having a value of 1. And then from the angle of pi over 2 to the angle of pi, my values are going from 1 to 0. So value of 1, and then less than 1, 1/2, smaller, 0. And then the other half is perfectly symmetrical. We're going to get the same sort of shape here, like that. So according to your textbook, or at least according, oh, there's a question. Sorry, there was a question before that I totally forgot about. No, sorry. Yeah, sorry, I missed that question before. Apologies, and I don't think it's worth going back. Yeah, okay. Yeah. So This type of graph is specifically what your textbook calls a cardioid, where I would say the thing you're adding and the coefficient of your trigonometric function cosine or sine have the same absolute value. So more generally, if you graph R equal to, I think they write it as, yeah, A plus B cosine theta, or R equal to A plus B sine theta, and A and B have the same absolute value, so the absolute value of A is equal to the absolute value of B, then you get this sort of shape. So for example, let's just draw another one. So let's pick something more interesting, like, I don't know, R equal to -2 plus 2 sine theta. So really, the only thing we have to determine as far as drawing this cardioid goes is kind of like which way it's pointing. It should have the same shape as the one we just drew, although dilated by a factor of 2, but that's about it. So again, I'm really just gonna pick the same angle values. 0, pi over 2, pi, 3 pi over 2, and 2 pi. My R values are going to be -2 plus 0, -2 plus 2, -2 plus 0, -2 minus 2, and -2 plus 0. So this one's kind of funky in that everything's going to be pointing in the opposite direction. So when my angle is 0, my value is -2. So there's my first point. When my angle is pi over 2, I get 0. My angle is pi, I get -2. So I start here, then here, then here. My angle is 3 pi over 2, I get -4. So here, then here, then here, then here, and then back to here. So it's going to look like this. Still the same shape, just oriented differently. So as long as that thing you're adding and that coefficient have the same magnitude, doesn't matter if they are the same sign or different signs, you're going to get this sort of shape, always. Now, things get weirder when these numbers are not the same. Yeah. So, and your book gives them fun names. Li limacons with an inner loop, limacons that are dimpled, or oval limacons. So, yeah. Yeah. Okay. So basically, here's the gist. You got R equal to A plus B cosine theta, or R equal to A plus B sine theta. You're going to get an inner loop if this equation has more than one solution to being set equal to 0. Here's what I mean. Let's say we had R equal to 1 plus 2 cosine theta. If I set this equal to 0, there's more than just one solution. I should say, there's more than one solution on the interval from 0 to 2 pi. So I set this equal to 0. 1 plus 2 cosine theta. Why am I writing the same thing again? That's really smart. 2 cosine theta equals -1. Cosine theta equals -1/2. And the angles that satisfy that are going to be theta equal to what? 2 pi over 3 and 4 pi over 3. So when we graph this one, here's what happens. So I'm still going to plot those same 5 points I like to plot. So I should probably draw this up here. R equals 1 plus 2 cosine theta. I'm going to get theta and R. I'm going to do 0, pi over 2. And I'm going to sneak in the right places my extra zeros here. But I'm not going to worry about them just yet. So let's see. So plotting these values, Cosine of 0 is 1. 1 plus 2 is 3. Cosine of pi over 2 is 0, so I get 1. Cosine of pi is negative 1, so I get 1 minus 2, which is negative 1. Cosine of 3 pi over 2 is 0, so I get 1 plus 0. And cosine of 2 pi is 3 again. So just drawing those out, 3, I get a 3 there, get a 1 there. But instead of getting a 0 here like I did before, when I point to the pi direction, I get a negative 1. And then in the 3 pi over 2 direction, I get a 1 again, and then back to 3. So I'm going to do this. I'm going to go here, and then to get to there, well, when theta is 2 pi over 3, I get 0. So when I'm pointing in that direction, I come down and I get a 0. I loop around, and then in this other direction, 4 pi over 3, I also get 0, and then loop back around, loop back around. So basically, if the B value is bigger than the A value, so if the absolute value of B is bigger than the absolute value of A, we get a loop. Let me show you what I mean. I mean, I know I just showed you. Like, let me show you how it works, even if you have less nice values. So for example here, so we said if B was, so there's the one we just graphed. But really, anything bigger than 1 will make that loopy, making me loopy. And as long as it's bigger, right, you still get a loop because you're still getting extra solutions to setting it equal to 0, even if they differ in signs. That didn't change it at all? That seems weird. Really? I'm very surprised by that. I wonder why that's true. Well, shit. That seems weird. What if we change this sign? Okay, that flipped the direction. That's kind of weird though, that changing the sign of that really doesn't matter. I'm very surprised by that. Sometimes you learn things. So if the coefficient of your trig function is bigger than the thing you're adding or subtracting there, you get a loop. If it's the other way around, you don't get a loop. So if we have something like r equal to 2 plus 1 times cosine of theta, you get what's called like a, what was that? Nope, sorry, that's too big. Apologies. So we have to go like 3 halves here. That's a dimpled one. And so I don't remember, I'm pretty sure though, I think the threshold here is if this number is twice as big as the coefficient there, then that's the threshold of where it's dimpled versus ovalish. So if I multiply it, well, in fact, obviously if I multiply everything by 2, so if I do like r equal to 3 plus 2 cosine theta, should get the same thing really, just stretched. So as long as this number is bigger than that number, I'm pretty sure you get a dimple. Let's see. Still dimpled? Still dimpled? Oh, I'm going the other way. I meant to go the other way. Sorry. Smart. Real smart sometimes. I meant to make this one bigger. Still dimpled. Still, but barely dimpled. So yeah, I think once you get right up to, I mean, you can barely see it there, but there's still the tiniest dimple there. But once you get to 4, not 34, right? You've kind of got this, you're not dimpled anymore. You've got a place where probably the tangent line there is vertical, where I'd be willing to bet a small amount of money that on this one, even though you can't really see it, there is an indentation. I believe it, but we'd have to do the math to prove it. And then, no, that was, oh, then, and then finally, once you get to be bigger, so if you have like r equal to, let's zoom back out again. I know this is not the most exciting thing, but if we have like r equal to, say, 5 plus 2 sine theta. You got to spell theta right, though. Don't like my theta anymore. Oh, I need the r. Apologies. No, doesn't like the way I did that. Try that again. There we go. Then it's ovalish, and it becomes very, very close to being circular. Circle. Yeah, fun times. So what I would say is if you have something like this, where it's a number plus a multiple of sine or cosine, it's going to be one of these snail things, the whatever the word was in French, limaçon. And depending on the relationship between your thing you're adding and your coefficient, you're either going to get a loop or a nice perfect cardioid or a dimple or an oval thing. I would encourage you all to look at the examples that Babson or the homework problems in section 11.4 that Babson posted, specifically numbers 21 through 24 in section 11.4, because those are what's kind of showing you what the threshold breakpoints are for the different things. And then there's weird stuff. So the last thing I'll say about this is all I ever had to graph. I know that's not like reassuring to you all, but like no one's, well, I shouldn't say that. I think it's weird to graph something like this. So does Desmos. That's reassuring, not at all, but that definitely is something that was in, let me see here. It was definitely in here. Yeah. Let me make it, yeah. Maybe I'm missing. No, that is definitely number 10. So cool. How do you graph that? Good question. So, yeah. Oh, of course. Yes. I mean, yeah, I know you're all very excited to watch me graph weird polar graphs, but yes, you're welcome to do this. So if I was trying to graph r squared equal to sine theta, your book does something weird. One sec here. Yeah. So they do something like this. Yeah, that is bizarre. I don't love it. Here's what your book does. So first of all, to have solutions, your sign better be positive, right? And sine is positive from 0 to pi. So from 0 to pi, your sine graph looks like this. And you're basically saying, cool, r squared is equal to those values. So pi over 2, r squared is equal to 1. So r is equal to plus or minus 1. But it's something like, say, pi over 6 over here, your r squared is equal to sine of pi over 6, which is 1/2. So r is equal to plus or minus 1 over root 2. So you get something like this, where when your angle is 0, you get 0. When your angle is pi over 6, you get either 1 over root 2, I'm just making up where it is, or negative 1 over root 2. And when your angle is, say, pi over 4, sine of pi over 4 is root 2 over 2. And then you get r squared equal to root 2 over 2. So r is plus or minus the square root of root 2 over 2. It just seems totally bizarre. But it's a bigger number. So at that angle, you're a little further out. And then at the next angle, you come back in a little bit, and you get this weird kind of like figure eight-ish looking thing. I think it's called a lemniscate. It's very odd. No, I don't even want to. I really thought Desmos was actually going to graph it. I'm curious what happens if we try to graph the square root of sine of theta. Let's just delete it all. What are you doing? Oh my gosh. All right. And then we'll get to the last thing here, real quick. And then, well, that is not at all the same. So it's very different. I wonder why that looks so different. Oh, because in this example, no, yeah. No, I don't know. Sorry. I'm gonna have to go think about it because, yeah, I'm very surprised. I know I already tried doing this, but like I feel like I should try it again. Nope. Like no dice. What's it say over here? Polar equations must be linear in R. Oh, okay. Well, how? boring are you? All right, so enough of that. I mean, unless there's anything you really want me to talk. Okay, there is one last thing. Finding the slope in polar coordinates. So finding slopes of tangent lines in polar coordinates. So let's look back at, I don't know, one of these lovely graphs I've drawn. Sure. Let's look at this loopy one here. And I would really like to find the slope of the tangent line right there. I'm really curious what the slope of that tangent line actually is. And that's at the point where theta is pi over 2 and r is 1. So right where, yep. So theta equals pi over 2 plus 1. So that's what we're going to do. We want to find the slope of the line tangent to r equal to 1 plus 2 cosine theta at r theta equal to 1 comma pi over 2. All right. So the way we're going to do this is the way we did it for parametric equations. With parametric equations, we said dy dx, the slope of the tangent line, is equal to dy dt divided by dx dt. Goodness gracious. But this time what we're going to say instead is that dy dx is equal to dy d theta over dx d theta. We're essentially imagining theta as our parameter instead of t as our parameter. But what about r? Well, in fact, how are we even going to get our parametric equations, right? Because to do this before, we had to have x as a function of t and y as a function of t. Well, remember how there's a way of going between polar coordinates and rectangular coordinates? That's what we're going to use. We're going to say that x is r times cosine theta and y is r times sine theta, which is still not great because I have an r, but we have an equation for r. R is equal to 1 plus 2 cosine theta. So our x equation is really 1 plus 2 cosine theta times cosine theta. And our y equation is really 1 plus 2 sine theta times, 1 plus 2 cosine theta, apologies, times sine theta. Which I guess we're going to have to use the product rule for. So our dy dx equal to dy d theta over dx d theta is going to equal, okay, so the derivative of y is going to be derivative of 1 plus, that's a cosine, believe it or not. Derivative of 1 plus 2 cosine theta, which is negative 2 sine theta times sine of theta plus 1 plus 2 cosine theta times the derivative of sine of theta, which is cosine theta, over dx d theta, which is going to be the derivative of that, still negative 2 sine theta, times that, cosine theta, plus 1 plus 2 cosine theta, times the derivative of cosine theta, which is negative sine theta. Could we simplify this? Sure. Should we simplify this? I don't think so. Because especially we're just going to plug in our values. So I don't think there's a good reason to simplify this. Let's go ahead and plug in theta equal to pi over 2. And hopefully we get a slope that is positive something, right? I don't know what it's going to be, but I'm pretty sure it should be positive. It looks like it could be maybe positive 1. I don't really know though. So let's take a look and see. We plug in pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So I'm going to get negative 2 times 1 plus 1 plus 0 times 0 over negative 2 times 1 times 0 plus 1 plus 0 times -1. And that's going to simplify to -2 over -1, which is +2. Okay, that seems plausible. So the slope equation for polar coordinates is really kind of gross, because what you're more generally doing is you're saying for r equal to some function of theta, you're letting x equal r cosine theta, which is your f of theta times cosine theta, your y equal r sine of theta, which is your f of theta times sine of theta, and then your dy dx is dy d theta over dx d theta, which both use the product rule. Your dy d theta is going to be f prime of theta times sine of theta plus f of theta times cosine of theta. And your dx d theta is going to be, bless you, f prime of theta times cosine of theta plus f of theta times negative sine of theta. It's not a formula anyone should memorize. This process of writing it down, I think, is easier than memorizing it. And there was a chat, though. Let me look at the chat here to see if there was something there that was needed to be addressed. Before taking the derivative, if we multiply the cosine and sine, would it make it better? I don't think so, because there was still going to be a product rule. Right? I definitely looked at that, but when I was looking right here, right, if we multiplied this out, yeah, it's cosine theta plus 2 cosine squared theta. I mean, I guess it's the chain rule technically. And here it's sine theta plus 2 sine theta cosine theta. I don't think those derivatives are really any better than the way we did it. So no, I wouldn't suggest multiplying it out here first. It's just kind of gross, but doable, right? This is definitely a thing you can calculate without too much effort. It is obviously worse if your angle is less nice to plug in. Right? So if you're actually trying to find some of the tangent line in a particular value and you have to plug in something like pi/3 or pi/6, you really have to know how to evaluate sine and cosine of those angles. Let's see. There's something else I had in mind here. Is that it? I know where it is. Let me ask you all. That's not it. There we go, right here. Let's make sure I've got all the things I've meant to have said. Yeah, that's terrible. That's a good question. I don't know the answer to that. In my heart, the answer is yes. In my mind, the answer is, do I have enough time? I will try to. Well, what I will really do is look and see what I already have and see if that is suitable. Yeah, that's it's on my mind for sure. I will try to. I just don't know if I would be able to. Yeah, that's definitely the goal though, is to make one. When's Babson's final? And when's Parlak's final? Okay, so we got a little bit of time. It's not Friday. But what I want to ask is, I think that pretty much is everything, all the content, at least covered by Babson. Again, I know I've done the Parlak students a disservice by not really have addressed what they were doing in class. Yeah, I don't see anything else here that's really super necessary to talk about. Yeah. You can find arc length and area of these polar coordinates as well. It's just not something that either class covered. So I feel like I shouldn't try to jam it in there for no good reason. There was one more thing though. Sorry, there was not one more thing we need to cover, just one more thing I need to address, because I remember looking at some of these homework problems and seeing one other thing that was notable here. Where'd you go? Yeah. Sorry, there was one other thing. It was something like, sorry, one second. I know I saw something that made me think I should mention that. Damn it. So there are, I'll say in section 11.3, there's a lot of going from polar to Cartesian, Cartesian to polar. So you should practice that. Um, damn it, where was the other thing? I thought I saw questions that said something about like talking about R. Yeah. So there was a question like, so here's a question on the summary exam that I thought was kind of interesting and also something you do later on. Um, it was question number 26 from section 11.5. It was sketch the region defined by the inequalities. So sketch the region defined by R going between 0 and 2 secant theta, and theta going from negative pi over 4 to pi over 4. This is definitely the kind of thing you do when you're trying to write a double integral using polar coordinates or a triple integral using cylindrical coordinates, which is just polar with a z. You're trying to describe some region in either 2 or 3 dimensions. So the idea here is we want to graph these things. Well, r equals 0, no big deal. I graphed it. It's the origin. R equals 2 secant theta, on the other hand, is a graph you want to be familiar with because it's something you actually know very well. Let's fix it. We're going to change it to being in terms of rectangular coordinates. So there's 2 things you can do typically to make something work. I mean, here there's a way you can do it without this. So if you see an R by itself is terrible. You don't want R. You either want R squared, because R squared is equal to X squared plus Y squared, or you want R times cosine, which is X, or R times sine, which is Y. And if we rewrite the right-hand side as 2 over cosine theta, it becomes obvious that we should multiply both sides by cosine theta and get R cosine theta equal to 2. Or in other words, X equal to 2. So here's the curve R equal to 2 secant theta. And then theta equals pi over 4 is this angle. And theta equals negative pi over 4 is that angle. Before I sketch it out, or sorry, before I sketch the region, yeah. The idea here is that you're essentially saying R goes from 0 to this 2 secant theta. So you have like radial lines shooting out from here, but they should stop right there. That's how you're defining this region as your R goes from 0 to 2 secant theta, and we go as far down as theta equal to negative pi over 4, and as far counterclockwise as theta equal to positive pi over 4. So that is your entire region, this triangle here. That's really the way we think about regions using polar coordinates. You've kind of got like boundaries for your angle, and then your R's are starting at the lower value, whatever they poke through, and ending at the larger value, whatever they poke through. That's all I want to say. Is that it's kind of weird though. Polar coordinates, they take time to get used to. Really, is the hard thing. And unfortunately, they usually don't get a lot of attention in 21B because it's like, it's at the end. Just cool. So for example, let's do one more. I could say, I want to sketch the region. Yeah, I like this. Okay. Defined by, let me something a little bit different here. Yeah, let's say we have R going between 1 and 3 secant theta. Sorry, not secant, I wanted cosecant, apologies. And theta going from, let's say, pi over 4 to pi. This might look really weird, so let's graph it. So with the practice we had, we should recognize that r equal to 3 cosecant theta is going to end up being y equal to 3. Because we're going to multiply both sides by sine theta and get r sine theta equal to 3, which is just y equal to 3. R equal to 1 looks like a circle of radius 1. Theta is going to go between pi over 4, which is this angle right here, to pi, which is this angle right here. So if I'm thinking about the part I actually want to shade, I'm going to start drawing radial lines shooting out from the origin, but I'm not going to actually start them until I get to the lower boundary of r equal to 1. And then I'm going to get all that, and then it's going to stop right there. So I'm just getting the bolded part of that green line there. Same deal when I go up this way, right? I'm not getting any of that. I'm just getting all of that. And so on. Getting that, 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 that. So I'm getting, so I'm gonna draw it again and shade it in. So it's gonna be all of this. Forever and ever and ever to the left. There is no end. Kind of weird. All right, that's really all I have to say. I know I keep saying that and I keep talking again, but I don't think I have anything else to say unless you all have questions. You guys like, don't ask any questions, you can go. You guys are welcome. You're free to go anytime you want. But if you want to ask questions, you're welcome to stick around and ask questions. If you don't, I get it. It's the end of the quarter and you're like, let's just get through it. So Thursday, I think the idea will be we'll review, come with questions, come with topics you want to talk about. Also, if you have something you really want to see or a thing, a topic you want me to talk about, shoot me an email and I'll be like, oh yeah, I can talk about that definitely. So otherwise, I'll come with review materials that I already have, and I will certainly look to see what sort of practice exam I can write. I assume Babson is giving you a practice final, just like he's giving you practice midterms. I don't know. Has Parlay been giving practice? No. Okay. So right, right. And I think her weekly practice problems are actually really good. So I mean, I think the content that Parlak has been delivering to you all in her class is excellent. And I think you all are probably, if you've been doing the things in the class, you're probably well prepared for whatever exam you're going to have on the final. As far as Babson goes, if you're doing the homework, great, but the homework isn't collected, right? Right. So it's always hard to keep doing the homework when it's not collected, but obviously you should be doing it. So yes, that said, I'll try to come up with something and I'll see you all on Thursday. And then as far as starting Friday, if you're looking for me in office hours, starting Friday office hours will be in the drop-in area in Shields Library, not in my other locations across campus. Not that I see many of you in my office hours, but in case you are looking for me, that's where I'll be. Not a dig, just an observation. It's fine if you don't come see me in office hours. There's lots of other resources.
Class?
Yes.
I couldn't find it.
Oh, so like from here, if you look at the quad, basically if you go up the middle of the quad to the flagpole, there's those stairs that are right outside of the entrance to the MU. You go up those stairs and it's just to the left, and there's like a big like thing on the window that says C class.
Oh, I went there.
Did you go inside? Was I there? What day was it? I'm only there on Wednesdays.
So I had.
Okay, but I am there on Wednesdays from 1 to 4. I don't think I've missed a Wednesday.
It was a Wednesday.
Okay.
That was
Yeah. maybe there was a day I had to miss. I don't know. Yeah, now I feel bad. I'm sorry to have directed you wrongly. Just to answer this question, the reason r equals 1 is a circle is because you're saying the radius is 1 and the angle can be anything. So you just go around. So yeah, r equals a constant is always going to give you just a circle with that radius. Because you're just saying, oh yeah, the radius is that number. So,
I just have a question, because like, I'm gonna be taking 21C
Okay.
this summer, so it's like a 6-week course.
taking it in semester 1, semester 2.
Oh, it's gonna be at a community college.
Oh, okay.
Yeah, so like, what are some skills or topics I should be like improving on?
Well, so it really depends because at the community college, it might be different content than what is in our 21C class here.
Okay.
I would certainly direct you to Grant's website, which have you seen it before?
Yeah.
So he's got good resources there if the content is the same, because usually our 21C content covers like oh my gosh, sequences and series, like the first half-ish, and like test for convergence and divergence of a series. And then the second half is like vectors and like distances between 3D objects and stuff like that. So,
Okay.
but it's really hard to say what you should actually be coming to it with because 21C used to be a very different class here before they changed the order of the content. So it's hard to know. Your 21C could be like double integrals and triple integrals because that's the way they're going to go first. So it's I don't have a good answer based on the fact that it's not the 21C class here.
Okay. Yeah, well, thank you.
That said, you're welcome to reach out if you have questions about it.
For 522,
Mhm.
I was here, but I don't think I filled out the.
Okay. I can correct that. You're welcome.
Also, could it take different parts of a series at different instances?
Oh, I don't know.
That's what I heard from one of my friends.
Yeah, that's a question I feel like I should know the answer to, and I don't. Yeah, I don't know. But certainly the point I just brought up would be a good reason why you shouldn't be doing that.
It's like different.
Right. Because maybe they're covering material in their third quarter of calculus that we already covered in our second quarter, or vice versa.
You're taking the similar speed.
In fall.
Let's hope I pass.
I hope everyone passes.
Okay, you want to email you?
Yes, because I'll forget otherwise.
I would.
You too. Hmm. All right.